We've looked at circuit basics, the Kirchhoff's laws for the loops and junctions, and how voltage and current behave in loops and junctions. Now we're going to look at series and parallel circuits and what that does to resistance before we put everything together and look at compound circuits after this. So we'll start with what a basic series and parallel circuit are. A series circuit is one where resistors are connected directly to each other with no junction in between. So instead of using resistors, this picture actually showed light bulbs, but they're next to each other. So they're in series, there's no junction, so you can see the wires the same the whole way around. Because there is no junction, that means that current has to be the same across each resistor. And your voltages are going to add up. So think of it this way. This is a loop, so your voltages on each of these have to add up to the voltage of your power source. And because there is no junction, the current's going to be the same across each resistor. What we're going to look at now with series and parallel circuits are something called equivalent resistances. And that's just when you're going to combine your resistors into a single equivalent resistance for the whole circuit. With series, it's pretty easy. I call this RS for equivalent resistance in a series. You're just going to add up the resistance of all of them. So R1 plus R2 plus 2 plus R3 plus however many resistors you have. So to get the equivalent resistance for circuits for resistors in series, you're just going to add them. Now for parallel circuits, this is when you're going to have two resistors connected at both ends. It's going to look kind of like a ladder. In a parallel circuit, you're going to have a junction. So because you have a junction, you're going to have a different current. In other words, your current is going to split between each junction. Voltage, however, is going to be the same across your parallel circuits. So remember, voltage in a loop adds up. That means that this is one loop, this is a second loop. The voltage here has to equal the voltage of the battery. The voltage here, again, there's nothing else that it has to add up to, is the same as the voltage here, which is the same as the voltage here. So voltage is the same in parallel, whereas current is the same in series. The equivalent resistance for parallel is written like this. I call it 1 over Rp for equivalent resistance equals 1 over R1 plus 1 over R2 plus keeps on going. The easiest way to do this mathematically is to use the inverse button on your calculator. So make sure you're just adding the inverses and then taking the inverse of your answer. It's important that you do not forget to take the inverse of your answer at the end. So that's how we find equivalent resistance. You'll see why this all matters once we start reducing compound circuits. Okay, so let's do one example and then we'll do a second one. The three resistors in the picture are connected to a 12-volt battery. What current is provided by the battery? So what we want to do here is reduce the circuit by finding the equivalent resistance of these three resistors which are in parallel. So to find the equivalent resistance for resistors in parallel, we're going to take 1 over Rp equals 1 over 58 ohms plus 1 over 70 ohms plus 1 over 42 ohms. So this equals, let's see, 1 over 58 plus 1 over 70 plus 1 over 42. 0.055 keeps on going, 1 over ohms. And then we want the inverse of that number. So the equivalent resistance equals 18.07 keeps on going ohms. Anytime I reduce a circuit, I like to redraw it. So I would redraw this right here down to a simple basic circuit with an equivalent resistance of 18.07 keeps on going ohms. And that's a 12-volt battery. Now we're just going to use Ohm's law to figure out what the current is. So V equals IR. Current equals V over R. So that's going to equal 12 volts divided by 18.07 keeps on going ohms. And this comes out to 0.66 keeps on going, amps. So we're not going to worry about sig figs with these just because there's so many numbers. I like to go to about 2 decimals with this. So the current is about equal to 0.66 amps. And that's the amount of current going through the battery. If I wanted to go back and figure out the current through each of these resistors, I can do that very easily. I know that because this is in parallel, each of these are going to have 12 volts. Actually, let me rewrite that over here. So this will have 12 volts, this resistor has 12 volts, and that resistor has 12 volts. And then again, V equals IR, so dividing each of those voltages by the resistance, so we do 12 divided by 42. This is about 0.29 amps. And then 12 divided by 70 is 0.17 amps. And 12 divided by 58 is 0.21 amps. If I add all of my unrounded numbers, I should get 0.266. And I do. So I have 0.66 amps going through the battery here, gets split at each of these junctions into about 0.21, 0.17, and 0.29, and then it adds all back up when it comes back around to the 0.66 amps. Let's do one more example. Which of the following 2 circuits will provide more power? So power, remember, in a circuit equals IV. I don't like that I. P equals IV. We have the voltage, we don't have the current, but we have resistances, so we can figure out what the current is from there. So we have a series circuit and a parallel circuit. We want to reduce both of those by finding equivalent resistance. Starting with the series, resistance in series is just equal to the 2 added up, so 18 plus 18, this would be 36 ohms. And then over here, the resistors in parallel, this would be 1 over 18 plus 1 over 18, and the inverse of that. So this equals 9 ohms. So knowing that power equals IV, and we know that I is going to equal V over R, we know already that the parallel circuit is going to have a smaller current, a greater current. So this will have a current of 1 amp, and this would have a current of 9 divided by 36, 0.25 amps. So which one will provide more power? The parallel one, because of the equal voltages and more current. So that's the basic for series and parallel circuits. The only thing left are compound circuits, and we'll get to those next.